So this lecture will be about phasor diagrams. So this is what we're talking about. We're talking about phasors, diagrams. All right, and I'll explain what a phasors diagrams are. Phasors diagrams are simply diagrams that show you the different phasors in a given circuit for all the voltages and the currents, and even impedances, if you're interested in putting those in there, in a complex plane. So phasors diagrams show you the different relationship between the different phasors in a given circuit in a complex plane. So just write it down. Phasors diagrams, or phasors diagram, are first and foremost diagrams in the complex plane. This is obvious because phasors are complex numbers. So in the complex plane that show you, the electrical engineer, electronics engineers, show you the different phasors in an AC circuit. By AC really means sinusoidal, right? So in an AC circuit, different phasors and how they are related or positioned. Positioned is more in relationship to each other one. So the key idea here is that we go, I forgot the complex plane. The idea here is to show you diagrams in the complex plane, or to draw diagrams in the complex plane, where all the different phasors will be included, and you will see how they are positioned in space in relationship to one another. This is what phasors. Now, before I even go on with phasors, I want to use here two memory hooks. So before I go to phasors, here's a couple of memory hooks. A memory hook is simply an artificial way that allows you to memorize something. Right, the memory hooks are Eli and ice. All right. In Eli, in the word Eli, the letter E comes before the letter I. This simply means that across an inductor, and the L just reminds you that it's an inductor. The voltage in an inductor leads the current. So voltage in an inductor leads the current. Just look at the letter Eli and you can see that the letter E comes first. Now across the capacitor, and the C here, it's to remind you that it's a capacitor. The current in the word C, ice, comes first and the letter E comes last. Now remember, E stands for voltage. E actually is the old word for voltage, which is called the electromotive force. This is a force that sets electrons in motion. A voltage is what sets electrons in motion in a given circuit. So that's where we got the letter E from. So it's a leftover from the days where we didn't use the word voltage, we used the word electromotive force. All right, so I'm going to just stick with the fact that electromotive force is nothing but an old way of saying voltage. So instead of saying electromotive force. Now the reason why VLI and ICV don't work, obviously, so that's the reason why we stick with E and then for voltage rather than V. It would fall flat if we use the letter V. All right, ice, in the word ice, what comes first? The letter I, so current leads voltage in a capacitor. The letter C reminds us that it's a capacitor. Current is represented with the letter I, and voltage is represented with the letter E. Ice. Ice, ice, baby. I can resist it. Anyway, I apologize. All right, so where did we get this stuff? Well, it's pretty simple, actually, to even prove to you and then show you the different diagrams. So we'll just keep track of, or keep the ice and the word Eli in the back of our minds and just show you Phasor diagrams. So I'm back now, and I'm covering Phasor diagrams. Now we can call it Phasor diagrams because there are a lot of phasors, or Phasor diagram because it's a single diagram showing you several phasors. I also call it Phasor diagrams because there are a lot of drawings. Whatever works for you, right? I'm not teaching English here, I'm teaching you electronics. All right, so to explain to you the Phasor diagram, I'm going to take a very simple example in here. All right, I'm going to take an inductor whose value is 30 millihenries. I doubt that you'll ever find this one commercially. I don't think that 30 millihenries is a very common value, but let's just say the L of the inductor, so the inductance of the inductor is 30 millihenries. Let's assume that there's an IL of t, and there is a VL of t, just like I have in this drawing here. Now, in AC, drawing arrows for voltages or currents is absolutely meaningless, but we can assume that this is a snapshot during 1/2 of a cycle, of a sinusoidal cycle. And it is true that during 1/2, the current will be flowing here and the voltage would be. The arrow of the voltage points to the high voltage and the tail of the arrow points to the low voltage. That means this would be positive and this would be negative. And since current always flows from positive to negative, this is what I would get at one particular point in time. Now, don't forget that the current is constantly changing in magnitude, obviously, because it's a sinusoid. It's increasing, reaches a maximum, decreasing. Same thing for voltage. But at one particular point in time, this is the direction of the current, and this is the direction of the voltage. So the arrow points to the high voltage, and the tail points to the negative voltage. That's really what the arrow really means. Anyway, so we assume that L is 30 millihenries. We assume that omega is, let's just say 100, all right, radians per second. All right, and let's say that I gave you the value of I. So I told you that IL of t is 2. That means the maximum current at one point in time would be 2 amps. So the current is fluctuating between -2 amps and +2 amps. What does it mean -2 amps and 2 amps? In fact, the maximum value the current will ever reach is 2 amps. But sometimes it is flowing from left to right, and other times it is flowing from right to left. This is really what the plus and minus do. But it really means that the current will never ever exceed 2 amps. All right, since we're dealing with sinusoidal things, this is sine of omega. Omega is 100, so 100t. And let's just say that the current starts with a phase of 17 degrees. Now, what would be VL of t? Well, we can very easily find VL of t by switching to the Phasor domain and coming back, right? Or I can do it the hard way, right? So remember, we're dealing with an inductor, so we have to Eli. What does Eli tell me? Voltage leads current. By how much? By always 90 degrees. So this is what's implied in here. It is always a 90-degree. All right. So if I have the current, so what is VL of t? Well, VL of t is simply XL times IL of t. This formula is not 100% true. You have to always include the what? The difference of phase, right? So VL is XL times IL with the condition that VL of t leads what? The current by 90 degrees. All right, so what is XL? XL is the reactance of the inductor, and we know that the reactance of the inductor is L times omega. What is L? 30 millihenries, and what is omega? 100 radians per second. Now this has to be converted to henries, so 30 millihenries is 0.03 times 100, so we just shift to the decimal place. 2 points to the right, and that gives me 3. So 3 ohms. So the reactance of the inductor is 3 ohms. So now I can go ahead and write VL of t. So VL of t is XL, which is 3 ohms. This is XL times IL, which is 2 sine of 100 t plus 17 degrees. Now, this came from I, but in order for us to get to VL, we have to add to it what? 90 degrees, because the voltage leads the current by 90 degrees. So VL of t now would be 3 times 2, which would be 6 volts, sine of 100 t, 17 plus 90 is 107 degrees. So we had VL, but it's kind of sloppy doing it this way, and this is the reason why we prefer phasors. Now, if we were to use phasors, you can see that everything flows normally. All right, so here's the time domain. And this one is the frequency domain, but you can also call it the phasor domain. Call it the time domain, phasor domain, wouldn't really matter, right? As long as you know what you're doing. All right, so here's my inductor. We know that the value of the inductor is 0.03 henries, which is nothing but 30 millihenries. So we have an IL of t in here, and there's a VL of t in here. Once we switch to the phasors domain, what happens? Well, the inductor is replaced with an impedance. We're going to call it ZL. It's a complex number. The directions, we're going to keep them the way they were. So this represents the phasor of the current, and this represents the phasor of the voltage across the inductor. Ohm's law applies equally to the time domain and the phasors domain. So we can simply say that VL, all right, equals ZL times IL. Now let's see, what is ZL? We told you that for an inductor, ZL is XL with an angle of plus 90 degrees. And this is the famous 90 degrees that shows me the relationship between current and voltage, right? Anyway, so what is XL? XL is simply L times omega plus 90 degrees. And we just computed L omega, and we found it to be equal to, what was it? Omega is 100, this is 0.03, so it's 3. So ZL is 3 ohms with an angle of plus 90 degrees. Now, what is IL? Well, IL, all we need to do is take the maximum, which is 2 amps, and we ignore omega t, which is 100 t, and we just keep the what? The plus 17 degrees. Now, it's just a matter of taking these two complex numbers and multiply them. So ZL times IL, which gives me 3 ohms with an angle of what? 90 degrees. This is ZL. And IL is 2, obviously amps, with an angle of plus what? 70 degrees. When you multiply two complex numbers, their magnitudes must be multiplied and their angles added. So ZL times IL is 3 times 2, which is 6. And obviously ohms times amps is volts. And the angle is 90 plus 17, which is 107 degrees. And since ZL times IL is equal to VL according to Ohm's law, that means this is VL. Now this is in the phasors domain. So if we go back to the time domain, what is VL? 6. So that's the peak voltage. The voltage across the inductor here will never ever exceed 6. That's the maximum it'll ever reach. Sine, it will have the same angular velocity as the current, so 100t. But now the phase is what? 107 degrees. And that's the beauty with phasors. Everything is included, and you don't have to remember which leads what in what direction. All right, that's pretty much it. So, sorry, this should not be a phasor. This is the expression of VL over time. All right. So this is VL over time. Okay. Now, if I go to a complex plane, here it is. This is the imaginary. Please remember that Im has nothing to do with the current maximum. Im is simply a convenient way of shortcut to the word imaginary. This Re has nothing to do with the equivalent resistance. Re is simply what? The real axis. So do not mix apples and oranges. I am here. This is not an index. It's I with the letter M next to it. Means imaginary axis. Re means real axis. Right? So I'm going to choose a blue color, and I'm going to represent the current. So the current is represented with this arrow in here. How long this thing in here? It has 2 units. So from here to here is 2. Okay? 2 units. That means 2 amps. Okay? So this represents IL. IL has an angle of 17 degrees, makes an angle of 17 degrees with the real axis. That's IL. Okay? Now, VL, I'm going to use a red color for VL, makes an angle of 107. All right, so these will not be up to scale, so just bear with me, guys. This is the phasor VL. Now, if this is 2, this should be 3 times longer. So I messed up here the sizes. So if this one is 2, this one is 6, because obviously magnitude is 6. So this magnitude here is 6. So it should be 3 times as long as what we have in here. Okay? And the angle that it makes with the real axis is 107 degrees. Now, if I take 107 and subtract from it 17, and I'm going to use now a completely different color, maybe some kind of yellow, that means that the angle between the blue and the red, if I start from here, and I move all the way to here, this is 90 degrees. But what you have here is a phasor diagram. That's pretty much what a phasor diagram. Now, what is implied in here is that these things are spinning counterclockwise at omega. So this is the angular velocity. Obviously, we don't include it, and they're all spinning counterclockwise. So let's say I set myself here. This is what I'm doing. I'm watching here, and since these are spinning, now they spin at the same rate. So if this one is spinning at a rate of 100 radians per second, this also would be spinning at a rate of 100 radians per second. So because they're spinning at the same rate, that means their relative distances, that means the angles between them will always remain the same. Now, as VL moves over, this angle here, 107, becomes larger. And this 17 becomes larger. But the difference of angle between VL and IL will always be maintained at 90 degrees. So if I'm watching in here, which one will cut in front of me first? Obviously, as they spin, which one cuts in here first? So VL gets in here first. And if I wait a little bit of time, what happens? Eventually, IL gets in here. Now, how much of it, basically, of time or distance in time in between the two? Well, we can simply say that a full revolution or full cycle is 360 degrees. So 360 degrees corresponds to one cycle. The difference between them is 90 degrees. So how many cycles is that? Well, that comes up to what? 1/4 of a cycle. Right? So what does this again mean? Well, it simply means that the voltage will always be 1/4 of a cycle ahead of the current. So let's just say it in here. The voltage will lead the current by 1/4 of a cycle. Again, what does this mean? Well, this is really what it means. I'm going to just draw the diagram. So let's assume that now instead of using phasors, I'm looking at things over what? Time. All right. We have our expression of IL of t. And IL of t was 2 amps times what? Sine of 100t plus 17 degrees. What does this 17 really degrees means? Well, it simply means that IL, instead of starting at 0, has been shifted slightly in here. By how much was it shifted? We can figure out what the portion, how much of a cycle. All we need to do is take 17 divided by what? 300 what? 60 degrees. And we would figure out by the quantity of a cycle that it has been moved by to the left. So this is IL. All right, so bear with me. Let's say that this is IL. So IL, pretty much what? It does not start at 0, but is slightly, this corresponds to that 17 degrees. Now, if we convert it to a time, it's not too complicated. We could do it. I don't feel like doing it, but there's a little bit of a shift. So this represents IL of t. How about if I wanted to represent VL of t? Let's just say I'm using a red color. Well, this is what it means. VL of t, by the way, is 6. Is it 6? I think it's 6. Sine of 100t plus 107 degrees. What does this really mean? Well, this is really what it means. 107 is 17 plus 90. It really means that when this one is at 0, the voltage is at its peak. When this one is at its peak, the voltage is at 0. When this one is at 0 going down, the voltage is at its negative peak. So say this is the peak of the voltage, and this is the peak of the voltage. When this one is at minus negative, the voltage is at 0. All right? So it looks something like this. So in red, I have the voltage. All right, more or less. Okay, so in white, so this is VL of t in red, and in white is IL of t. Now, if you look at them, which one reaches the peak first? Well, VL reaches the peak in here, and IL reaches the peak in here, which simply tells me that the voltage leads the current by how much? Well, if from here to here is one cycle, from 2 consecutive peaks, and if you do the math, this is 1/4 of a cycle. Right? this is really what it means. There's a 90 degrees between the voltage and the angle. So the voltage will always reach its peak or its zero 1/4 of a cycle before the current does. And this is always neatly illustrated in this diagram that is a little bit less confusing than what we have in here, although this one is not too confusing. So this is what a Phasor diagram is. Now, this example, I used it for illustration purposes, and I used an extremely simple case where we have just an inductor, and then we're looking at the voltage and the current across that inductor. Later on, I'm going to upload even more videos where we look at a little bit more complicated cases. For example, a resistor in series with an inductor, and then a resistor in series with a capacitor, or we might even take into account the more general case where we have a resistor in series with an inductor, which in turn is in series with a capacitor. Okay, so for now, I'm going to sign off, and then I'll send you the other videos later on.